So today for the MERL Seminar Series, I'm extremely delighted to welcome Dr. Petar Veličković for the talk. Petar is a senior staff research scientist at Google DeepMind, as well as an affiliated lecturer at the University of Cambridge. He holds a PhD in computer science from the University of Cambridge at Trinity College. He is very well known for his work on graph attention networks that many of us use frequently. He is also a pioneer in the area of neural algorithmic reasoning, where the goal is to align neural networks with classical algorithms. His papers were inspiring in my own efforts into bringing up this topic as a MERL KK over the last couple of years, and we had the pleasure of having his keynote at our multimodal algorithmic reasoning workshop at CVPR last year. Today, Petar is going to tell us about his recent work on amplifying human performance in combinatorial competitive programming. Without any further delay, I would like to welcome him for the seminar talk. Petar, please take it away.
Awesome. Thanks so much for kindly inviting me to speak to you all, and open generally for being really supportive of various works working in the domain of algorithmic reasoning, which I'm myself very much part of. And thank you all for coming down for my talk today. As mentioned, my name is Petar. I will be telling you about a recent bit of work, which I would say makes a pretty meaningful step at achieving one of the big aims I have for the future of AI development. I hope you will find the discussion interesting. I would say that given how the talk timing and constraints are set up, I'm more than happy to be interrupted midway. And in fact, if you see something that's confusing and you want to discuss it right away, please do raise your hand, and I will stop at certain points and check if there is anything worth picking up on that we can catch in the moment. And my aim is just, to have an interesting conversation with you all about how to build systems like these, what it might mean for future of competitive programming and programming as a whole, and things like that. So the specific result we're going to talk about, you can see it on this slide. We have released a paper on the archive in December last year, which has the same title as this talk, Amplifying Human Performance in Combinatorial Competitive Programming. This will be the main result I would like to present you with today. But that being said, it is basically going to appear at the end of the presentation, because I do feel like at the same time there's a lot of really important context behind how we ended up chasing this result in the first place. And also it gives me a nice opportunity to showcase a lot of other pretty exciting work that myself and several of my colleagues at GDM have been working on over not only the past months, but also past years, which are, kind of to show how this work in competitive programming is really just a culmination of many years of efforts into amplifying human capabilities with artificial intelligence, which is really something that we are really, really excited about. So I'll show you three works, the last of which will be the combinatorial competitive programming result, to sort of set the stage on how we arrived there. So I've been excited about producing tools that assist humans with artificial intelligence for a very long time. But the first tangible impact I've managed to make in this space was through our work, which used artificial intelligence to help mathematicians do their research work. And this was a paper that was published in 2021, so more than 3 years ago. And how did we set this up? So for me personally, I once studied in a mathematics-oriented high school. There was a time when I really wanted to become a mathematician, but spending some time around very talented mathematicians made me realize that this is probably not the best career path for me. But perhaps there is a way in which I can use something that I am good at, which is computer science and AI, to help a mathematician do something that they wouldn't be able to do on their own. So how do we imagine this interaction going on? Let's say a mathematician in the process of their work has to study really complicated objects. So let's say these are objects you might be able to write code to generate them. But okay, you generate them and they come out as this really complicated tangled graph structure where, no human can easily make sense of what's happening. And you are not satisfied with approximate results because, you need to be able to prove that whatever you've seen is actually meaningful. So the AI system will then ingest a graph structure like this and come back with some proposals about which parts of this graph structure might be most important for the specific problem that the mathematician is trying to solve. I must stress that the outputs of our AI system are nowhere near as clean as this slide implies. In fact, they were very messy, but already it is much easier to look at a subgraph of maybe 10 to 15 nodes as opposed to looking at a big structure of thousands of nodes for a human. And indeed, our math collaborators, when they were looking at the substructures coming out of our AI system, which used, by the way, a very rudimentary saliency technique, they were able to figure out that very often when faced with graphs like these, the system was really zoning in on these diamond-like structures towards the bottom of the graph, and therefore they hypothesized, oh, these diamond-like structures might be really meaningful. And this kind of spark gives the mathematician an idea, and sometimes based on that idea, they are able to prove theorems or even lay foundations for new conjectures, breaking new grounds in mathematics. And with this pipeline, we've been able to meaningfully impact not one, but two disparate areas of mathematics, knot theory and representation theory. And this was recognized by the journal Nature. In December 2021, our work was on the cover page of Nature and was reasonably well covered by the popular press. Although, to be honest with you, what resonated most with me is not these kinds of accolades, but how did the mathematical community respond? Because if you remember, my main aim was to make something that mathematicians could find useful. And I would say we've had a really good feedback loop from mathematicians on this work, specifically our Nature reviewers who are mathematicians. You know, normally reviewers for any conference, let alone a journal like Nature, the job of the reviewer is to, write critical things about your work. But in this case, the mathematicians basically from the get-go said, this is a new phase in use of computers in math research. I cannot imagine a mathematician not using these methods if available to them. And, this is really the crux of it. And also going back to kind of my personal old dreams of becoming a mathematician, we were able to then take the findings that made up this Nature paper and publish them in top-tier mathematical journals. So this particular paper uses these diamond structures I showed you before to make new progress on a 50-year-old conjecture in an important part of representation theory, which we've done together with Geordie Williamson, a mathematician at the University of Sydney, who kind of drove all of this progress together with us. But, it's not only that we were able to publish this paper, but this paper then led to a lot of follow-up works. And actually, one recent bit of work that I was quite happy about actually proves something that we've conjectured using the structures that came out of the AI system. So they prove it in a particular special case. And another thing which was quite cool is that as a consequence of the way things are named in mathematics, they've referred to our result as a BBDVW conjecture, or Blundell-Boosting-Davies Veličković-Williamson conjecture, and they also named a polynomial after us. So, in the process of doing all of this, I, without a very strong post-high school mathematical training, have been able to get a polynomial named after me. So this is something I was quite excited about. So that's one particular area. Another area which you might have heard of recently, which is also a very exciting area, but for a very different reason, is using artificial intelligence for football analytics through our Tactic AI paper, which maybe some of you have heard about before. So we've tried to use AI to improve football analytics, and we've done this through a very long-term collaboration with the Liverpool Football Club, which is one of the best football clubs in the world. And this is a picture from back when we visited Liverpool at their training grounds to kind of work on a hackathon to deploy a better version of our AI methods to help them drive decision-making in football analytics. And it's really a culmination of several years of research and several papers, workshops, and podcasts being published that resulted in the Tactic AI paper, which pulls together all the knowledge we've learned over the past 5 years and constructs a full AI assistant that's capable of assisting with football tactical decisions. And this work we've done in collaboration with Liverpool was seen as significant enough by the scientific community that we were able to publish it in the journal Nature Communications, which, as far as I know, is the first or one of the first times a sports analytics paper made it to this tier of Nature journals, which obviously we were quite happy about. I see there's a question on whether this correlates with their strong performance in the Premier League this year. I am unable to say because our collaboration basically ended after this work was deployed. They did promise us that they might tell us 1 or 2 years after they use it for a particular result that they've done this. But, the technology is with them. It is up to them how they use it. I'd like to believe that some of the things we've done together have made a meaningful impact in their tactics for this year. Okay, so what can Tactic AI do for you? Without diving too much into the details, you can find a lot more in the paper if you'd like to read about it. And we've open sourced a huge chunk of the code as well. Tactic AI starts off with basic predictive modeling. So being able to predict in a particular situation in football what is going to happen, who's going to receive the ball, whether there will be a shot or something like this. This is something that's useful for your usual data science machine learning pipeline. But then once you train a model to accurately predict what's going to happen in a football situation with reasonably high accuracy, that system had to have learned meaningful representations of the players. And then we can kind of feed those representations in a retrieval system. And this is where you can actually start to accelerate the work of humans. Because, for example, we studied to a huge extent corner kick tactics, as you can see in the figure in the top left. And basically, what you can do, right, is a video analyst, typically in preparation for a match against an upcoming opposition, has to look at huge quantities of these corner kicks scenarios to best prepare the team for the patterns that their opposition might play. And basically, often you have to do this by hand. So you watch one video, then you watch another video, and it's a really cumbersome process, and you have to rely a lot on your intuition for what to watch next and which sets of videos to watch. But if you have a nice retrieval system that's based on embeddings like our system, you can just retrieve the closest embeddings and therefore recommend to the video analyst what are the most meaningful next videos to watch. And this is something that can very tangibly accelerate their work. And then once we're able to do predictions and retrievals, we can also do generative modeling. And you can see an example of this in the figure in the top left, where the system is basically capable of proposing adjustments for defensive players, for example, to reduce the chances of a goal-scoring opportunity. And this is something that coaching assistants can directly leverage. So you feed a situation into Tactic AI, and it will immediately, in a couple of seconds, recommend where should different players be differently positioned. So change in position, change in orientation, change in velocity. Of course, the aim of this is not so much to propose exactly new tactics. We've deliberately made these changes to be relatively small scale, but they will immediately tell you, so you don't have to manually hunt for it. It'll immediately tell you which players might be critical to a success or failure of a particular tactic. And this frees you up to spend more time actually doing the decision-making and the creative part of coaching and less time, pattern matching. So we really believe that with this complete system that can answer these 3 types of questions, we have been able to influence the entire stack and accelerate the work of humans working in these clubs. And really the takeaway here, and we have lots of human case studies to kind of complement that with coaches from the club, that you should take away that Tactic AI is really a full artificial intelligence system that gives useful tactical suggestions to coaches. And the significance of these results has not gone unnoticed in the media as well. We've had a good bunch of media coverage of our work from the Financial Times, New Scientist, The Athletic, which is part of the New York Times, El País in Spain, and so on. One which I would say distorts reality a little bit, but is a nice passage I found, was this Wired article which said that the most exciting young coach in soccer might actually be at Google DeepMind rather than one of these other clubs. Okay, so I hope this gives a nice setup of how we try to work together with our collaborators, with different groups of researchers and analysts to find techniques where AI can very meaningfully amplify the human capabilities. We're not looking for AI that replaces humans. We're looking for AI that helps humans do their job a lot more efficiently. And in light of that, we jump to the third topic, which is AI for competitive programming. which really relies on a dream I've had since I've started working in artificial intelligence. Prior to starting my work in AI, I spent a lot of time in competitive programming. And, I wasn't the best competitive programmer ever by a long shot, but I like to think I was fairly decent. This is me together with a club, with a team from Cambridge that I was coaching at an ACM ICPC regional, which is basically a contest gathering the best competitive programming teams of university students in Northwestern Europe. So this is UK, Sweden, Finland, Germany, and so on. And on this one particular year, the team which I coached was able to win first place. And this is the team at the time posing with the winning trophy. And I was really keen. I'm not really in the level of the top tier competitors, but I believe that I have a decent level of knowledge in this space and a decent level of care, because I've poured a lot of years of my own life to train to become a better competitive programmer. And it would be really interesting to me to see how could we build an agent that's capable of outperforming me in such a contest. Well, that dream has sort of been achieved in December 2023 when AlphaCode 2 came out. It's placed at around the 87th percentile of all human competitors in Codeforces, which is a competition platform. And I am roughly at the 87th percentile in terms of my ELO rating. So yeah, basically since December 2023, this wasn't really my objective. There already exist LLM-based AI systems that were able to match or even exceed the level that I have. But then kind of aligning myself with the previous goals and previous objectives, can we maybe now use the fact that we now have really good code writing agents to maybe meaningfully improve the performance of human competitive programmers? And this is what became the next challenge. It actually took us a while before we found an opportunity to do that. But through the release of the FunSearch method, we have found such an opportunity. And now I'm going to take some slides to introduce FunSearch to you, because while it is not a topic that I have personally worked on, I'm not a co-author on the FunSearch paper, it is the beating heart of the system that we used to achieve the results I showed you at the beginning. So really, it's important to understand how FunSearch works in order to understand how we've achieved these results. So one of the main remits of Google DeepMind's computer science initiative is to discover new knowledge and efficient algorithms for impactful problems with the help of AI. And FunSearch is one of the first milestones in this objective. So with FunSearch, the researchers have been able to discover brand new knowledge and also efficient algorithms using that knowledge. And the way it works is it really tries to ramp up the capabilities in optimization problems where you have basically a really fast way to check how good a particular answer is, but it's really hard to solve it, perhaps because the problem is NP complete or NP hard or something like this. So the way in which FunSearch works is, assuming that you have a problem which is well expressible in this way, you have a large language model that can generate solutions. And the key thing is, if you let this large language model run rampant by itself to try to write an answer to a hard combinatorial problem, it is likely going to get stuck and not give you very useful insights. Because, you can have smarter and smarter AI systems. This won't let you solve P versus NP, right? So there is a sense in which these kinds of problems cannot be perfectly solved in an efficient time frame. So rather, the way FunSearch does it is it takes a large language model which can propose possible solutions and wraps it in an algorithm which controls it and makes sure that you don't drift away, produce gibberish solutions or solutions that won't work over a long horizon. So this evaluator basically guards against propagating incorrect solutions and also helps you iteratively evolve better and better solutions. So a specific problem I'd like to showcase to you, just to show you the power of FunSearch, is the CAPSET problem. In the words of Terry Tao, it is one of his favorite open questions, maybe his favorite. And the task is quite simple to formalize. You are looking at a 3 to the D grid, so a D-dimensional space where in every dimension you have up to 3 points, 3 integer points, and your question is to find the CAPSET. What's the biggest number of points you can take such that no 3 of them are collinear, right? And that means, so the space you're working with is a d-dimensional integer space, and you have modulus 3 in every single dimension. Okay, so to understand this problem better, let's study it from kind of a simple a special case kind of angle. Let's look at the one-dimensional version. Obviously, in the one-dimensional version, you can take 2 points. Taking the third point would not work because those 3 points would be collinear. And therefore, in d equals 1, the solution to the CAPSET problem is 2. In a two-dimensional version of the problem, here are some grid lines drawn for easier following. You can wander around a bit and convince yourselves that actually you cannot do more than 4. So 4 is the maximum number of points you can include in your solution before including additional points would result in collinearity, in 2 dimensions, that is. In 3 dimensions, you can still solve the problem. It's combinatorially tractable, and you can find solutions of size 9. So 9 is the biggest number of points that you can include in a 3-dimensional version of the CAPSET problem without causing any issues. Okay. But what happens for general dimensionalities? As you might imagine, this problem is exponentially growing with the dimensionality of the problem, and quickly it becomes intractable to try all possible solutions. And in fact, for all dimensions greater than 6, we actually don't know what is the optimal CAPSET size. There exist some constructions which give us a lower bound, but can we find even better ones? This is the type of problem that FunSearch is really well positioned to handle. And why is that? First of all, you can verify correctness very easily. So if you have a bunch of points that's a candidate solution, you can check, is there a line connecting any 3 of these points or not? This is a polynomial time procedure. And you can also measure, assuming you pass correctness checks, how good is this solution? So how many elements are in the set of points? These are both very easy procedures to do once you have a candidate solution. So this means you can write an evaluate function, which is quite efficient. And then you can use the large language model to guide searching for the best program in the code space. So here is how you'd set up a simple FunSearch prompt where you have first some methods to build a candidate set given a particular dimensionality. And you have an evaluate function which takes a built set and then evaluates it as to whether it's correct and how many points are in it. And you can see that the build function relies on this subroutine is in set, which effectively is what we want to evolve. So for a particular point, it checks, is that point inside the CAPSET or not? Returns true or false. And what FunSearch can do is it can take, say, a version 0 of this function that you provide it with, and it tries to write an evolved function. So this will be a prompt. What you see here is going to be a prompt for a language model that has to write v1 of this function, given the v0 and given all of the other functions. So the LLM will try to do that, and it might end up discovering a better solution for the constraint here in 2 dimensions, for which points to include in the CAPSET. And what you can do then, obviously in 2 dimensions, changing the function in this way grows your CAPSET from 2 points to 4 points. And what you can do then is you can feedback v1 to become v0 and rerun the language model again to try to evolve the solution again. So this is a procedure that you can kind of keep iterating on, but naturally, if you keep doing it kind of in a straight shot way, the LLM might get stuck. So what happens in practice is we can rely on evolutionary search, like a genetic algorithm, where we try many possible generations from the LLM, and we kind of iteratively chain them to arrive closer and closer to our optimal solution. And when you do things in this way with the right genetic algorithm as the wrapper to the LLM, we are able to actually reconstruct all the best known bounds of the CAPSET problem in different dimensions. But as you amplify the number of dimensions, actually FunSearch is capable of beating the previous best known lower bounds. So already in 8 dimensions, there is a big difference. From 496 points, which was the previous best known solution, to 512. And what's also interesting is because FunSearch provides a code implementation, you can sort of take the idea of this code and see how well will that code generalize to a bigger number of dimension as you go towards infinity. And actually, so not only were there specific cases where the bound was improved, you were able to take, the mathematicians were able to take the insights from the code and arrive at a better lower bound as a function of the problem size. So from 2.218 to the power of n to 2.2202 to the power of n. And one reason why these kinds of solutions are more approachable for a mathematician, for example, is because normally you look at a solution as just this raw collection of points, but FunSearch doesn't give you that. FunSearch gives you code, and code is much easier and human readable than the collection of points that it outputs. And it's much easier to spot patterns that way. So to the best of our knowledge, this is the first scientific discovery ever made using a large language model, in the sense that it's a provably new piece of verifiably true knowledge about a relevant scientific problem in mathematics. And it's a new computational paradigm. So it's a new way of using computation to discover new understanding rather than just facts. And in the words of Jordan Ellenberg, who helped the FunSearch team in deriving this result, the solutions generated by FunSearch are far conceptually richer than just a list of numbers. When I study them, I learn something. Okay, I see there's a hand raised. So
yeah, Petar, I have a question. Was this LLM trained in any specific way that it leads to a solution to the CAPSET problem, or is it a generic LLM?
So when the FunSearch team first made their solution, the LLMs at the time were not yet good enough at writing code. So this particular model of the initial Nature paper was a Palm 2 model fine-tuned for code execution and generation. But modern LLMs have bridged this gap, and you can reconstruct this result very easily using generic Gemini Flash models of the current class. So it used to be necessary to fine-tune code models, but now it's not necessary anymore.
I see.
Yeah.
Thanks.
Okay. So now that we've covered this result, and hopefully it becomes a bit more evident how you can use it to improve the performance of humans in these kinds of NP-hard combinatorial contests, we basically, my team identified this opportunity and realized that there exist many famous combinatorial contests like Google's hash code, which basically require you to solve a problem inspired by a real-world engineering challenge in a way that is NP-hard. So you cannot easily write an efficient code that will just one-shot solve the problem, and humans would not be able to either. I see there's another hand raised. Is there a question?
Yeah, just a reality check. Is the LLM predicting the output of the code, or is the code actually getting run? And if the latter, what's the stopping problem? How is that addressed?
So the LLM outputs code, which is then executed, but I did not completely understand the question.
Well, so the code is not guaranteed to ever finish running, right?
Yeah, of course. There's a timeout. So if your code takes longer than, say, 30 minutes to run, it's assumed to never terminate, which, of course, is a loose approximation, but still.
Okay.
Yeah. All right. So the way we felt this could improve human competitors in this particular regime is a competitor can implement something simple like a greedy algorithm, which, while obviously not being optimal for many choices of greedy strategies, you could, if you had a good enough oracle function, construct a greedy algorithm that would retrieve optimal solutions. And then you build a really simple, trivial scoring function, which tells the greedy algorithm what is the next element to take or what's the next step to take. And you ask FunSearch to evolve that using the same strategy I showed for the CAPSET problem. And this is a good kind of back and forth pipeline where you might get some evolved scoring functions which score better on the problem. Maybe there's some insight inside these scoring functions, which then prompts the competitor to try a different base strategy or even strap on additional local search or something like that on whatever comes out of FunSearch. And the idea really is that this mimics a real competitor's workflow in these combinatorial contests, because usually the way most top-tier competitors approach these combinatorial tasks is they will start by writing these three parts, right? They will parse the input, they will write the basic backbone with a very simple greedy algorithm, and they will write an evaluator so that they can hill climb on whatever comes out of that evaluator. The FunSearch part really automates this ingenuity of like, what is a good greedy strategy to follow? And it's basically a human AI synergy. So this system relies a lot on the skill of the competitor to find the right environment for FunSearch to thrive in, because if you don't have this good backbone to guide you and a good kind of genetic algorithm backbone to make sure you don't stray in a random part where your code doesn't compile at all, the system cannot achieve the best performance that it possibly can. It's really the synergy between humans and AI that makes this happen. So we took this approach and we deployed it on every single online qualification round of Hashcode from 2015 to 2022, after which the contests were sunset. And we were quite happy with this. The teams that we were competing against effectively here, obviously not in real time, involved some of the best competitive programmers in the world. Some of them had ELOs of approaching 4,000. My personal ELO is 1,900 to be precise. And in several of these years, we were able to outperform all the best solutions that human competitors were able to find throughout the contest. And even in the contest where we weren't able to, we were still in the top percentile. So the top 1% of all competitors. And, one argument you could make to this is maybe we just have enough skills to write a really good solution ourselves, and FunSearch just amplified that. This is for comparison. Back when I was a competitor, I participated in some of these competitions, and these were the ranks that my team was able to achieve. So in every single one of these cases, FunSearch grossly outperformed what I was capable of doing by myself or in a team of like-minded people. A good example also is 2021. This was the year when I took part in organizing Hashcode. So the rank of 20 is actually the best score that was obtained by Google employees over the course of 2 weeks when we tried to break the problem as much as possible before the contest started. So if you ranked all the best Google solutions against the competitors in that contest, you would have achieved the rank of 20. Hashcode outperforms that as well. So I would argue this gives a pretty clear sign of ability amplification of something that I would never have been able to achieve if I didn't have access to a tool like this. And to illustrate how the setup works, I'm going to focus on just one of these years for the time being, one which is arguably easiest to explain, and it's the first one where we achieved this rank 1 result. It's the self-driving ride problem, where you have different cars in this Manhattan-style grid, and the cars are self-driving, and you need to schedule them to complete different rides. So you have basically different users wanting to ride from one corner to another corner, and you have a fleet of cars that you need to then distribute so that a car kind of goes to a human takes the car drives them to their destination, and you need to kind of finish as many of these rides as quickly as possible in the given time frame that you have, right? So it's a very interesting, challenging combinatorial optimization problem, and not very tricky to describe. You assume that these are basically the streets of Manhattan, and the cars basically follow Manhattan distance when traveling from one point to another. So how did we set this problem up? We first start by making a class for all of our data. So we have here all the rides that the users have requested. So you have the starting point and the ending point. And for each ride, we also know what's the earliest time it can start. So that's the time when the user has called for this car, and the latest finish. So the time by which, after which the user will give up and stop requesting the car. And you can compute both the length of the ride as the distance from start to end, and also the distance to start. So if you have a particular coordinate, for example, a location of a particular car, you can easily, for convenience, compute the distance between the start of the ride and that particular coordinate, and the distance function, which is just simple Manhattan distance. Then we have a simple file parsing procedure, which just takes the input file, parses it in the same way you would in a particular contest, and just extracts all the meaningful data from those files. And your evaluation function, which for a given collection of ride assignments, so the way in which the output works here is you assign different cars to different rides. this procedure just simulates what's happening inside the solution. So as long as there is still time, you have this while true loop. You pick a particular car, and then for that, which is the earliest available car, you maintain a heap structure to see at what times different cars are available. And you then call this pick ride function, which is what FunSearch will optimize, that chooses for the currently selected car which ride it should go to, and then just simulate what happens as a result of completing that ride. And the pick ride function initially starts from a really, really simple solution, which is literally just iterate over all of the rides requested. And the first ride you find, which is finishable by this car, in the sense that the pickup time would be greater than or equal to the earliest start. And also the duration of the ride would be before the latest finish. You just return that. So this car will be sent to attend to this particular ride. And if you fail to find any, you just return -1, which means this car cannot be assigned to any rides at this point. And this backbone is actually quite silly compared to all of the competitors competing in that particular round. It has a below 20th percentile result, so it's in the worst kind of 15 to 20% of all competitors. But already after 2 hours of letting FunSearch evolve this pick ride function and leaving everything else exactly the same, we are already on the boundary of the teams that were able to make it into the finals. And if you allow this system to evolve for a little bit longer than 2 hours, it can actually outperform the top human team at the time. This is a pattern that we can replicate on all 8 of the contests we've tried. We haven't been able to reach rank 1 on all of these with the backbones we played with, but in all cases, we are able to land in this green strip, which is where the top 50 teams that would have qualified into the finals for that year would have been. And this is a result that we thought was quite significant, and actually some of the important faces in the world of competitive programming have agreed with us. This is actually the first time I was able to have a chat with Petar Mitrichev, who is one of the best competitive programmers in the world, and he said that this is an exciting approach to combine human competitive programmers with LLMs to achieve something that neither of them would achieve on their own. And Przemek Pietrkiewicz, who is actually the lead organizer of the hashcode contest that we used, actually kind of posited a claim that this could be seen as a sort of deep blue moment for competitive programming, which obviously we were quite happy to have this particular comparison in place. You might be interested to look at what kinds of solutions FunSearch comes up with. It's not easy to kind of go step by step and interpret what these solutions are doing, but this is just to show in the particular case of the 2015 hashcode contests, where you have to optimize the placement of servers in a data center. You start with this backbone simple solution, which is simple but scores already 348 points. After 2 hours of evolution, it's already the second best solution. And the solution grows in complexity with many different edge cases being checked. And you let it run for maybe a couple more hours, and it reaches this particular monster, which is by far the best score that was achieved on this particular problem. So you can see how even though it's a fairly constrained environment for growing the code, FunSearch can really make the most of that environment and just go at it and have some really nice outcomes. Now, one very obvious criticism you could give on these results is that all of these contests happened in the past. Okay, I see there's a hand raised, but I'm almost done with the slides, so maybe we can take that in a couple of minutes. So you might raise the criticism that, even though these are NP hard problems, even though that the humans participating in these contests haven't been able to achieve these kinds of scores, codes for these problems have still landed on GitHub, and people could have landed in LLM training data, even though, once again, here it's a very different setting for the LLM, and you have to kind of evolve code that's conforming to a particular backbone. You might still claim that because these contests happened in the past, the LLM had an unfair advantage. So we were using Gemini 1.5 Flash, which was a very recent model at the time when the results came out. So we had a very small selection of contests that happened after that model was released, but we decided to try it anyway. And we looked at this AdCoder heuristic competition 39, which was one of only 2 contests, I think, that came out after Gemini 1.5 Flash came out. And it's a really interesting combinatorial optimization problem where you have this 2D grid with red points and blue points, and you have to fit as many, you have to find a polygon that fits as many red points and as little blue points. And this polygon must be with all of its edges horizontal or vertical. So a standard strategy, which many teams employed, and we also employed in our approach, was to partition this space into a grid of cells. And then we hunt for basically a good connected subgrid, which encompasses as many red points and as little blue points as possible. And the way it works is our solution will kind of have a scoring function for every single cell. And we first pick one cell, that's our initial cell, and then we expand from there to always pick a neighboring cell to the currently constructed polygon, which has the highest value. So that's kind of how our greedy algorithm works. And much to our happiness, even though this contest happened in the future, so nothing about this problem made it into the training data for Gemini Flash, we were still able to quite reliably hill climb on the score. Of course, you get different fidelity and accuracy of the solution depending on how big your cell size is. So as you make the cell sizes smaller, you might hope to have a better score because you're able to have a bit more wiggle room in this 2D grid. But regardless of which choice of base cell you have, the scores tend to go up. And one thing that's really interesting is that when you start to analyze some of the final solutions that came out of FunSearch, you find that it basically just by itself, by trying to optimize the solution, learns some really interesting blocks, especially this block in the middle, where you see how it basically tries to look at a 30 by 30 subgrid centered at a particular point and kind of has a distance function based on how far away the different points are. It's basically trying to fit a tiny Gaussian around that point to see how close is this to a cluster center, which is really cool because if you look at these points, the way the data is generated for the contest is you take a mixture of Gaussians and you sample a point based on a particular mixture. And the model was never told that this data has a Gaussian structure, okay? So just through the process of hill climbing, it tried and kind of it stuck with it that maybe it makes sense to have like a local fitted Gaussian around the particular cell when deciding should I expand on this cell or not? How close is it to a cluster center? And that's pretty cool that this emerged just through evolutionary programming and LLM prompting. This solution, with a 95% confidence interval, we're able to bootstrap it as being ranked roughly in the top 10 of all of the entries. I should stress that all of the top entries in this contest used an additional simulated annealing block on top of the greedy algorithm. So the fact that we were able to achieve such a high score without any simulated annealing whatsoever is already a pretty impressive result, and probably something we could even further iterate on if we allow ourselves local search on top of this solution. So TLDR, what we believe we have on our hands is a state-of-the-art methodology for AI-assisted combinatorial competitive programming based on FunSearch, and it's capable of achieving top percentile results in historical competitions, hopefully making a very meaningful step towards a tool that can actually be used by participants in these combinatorial competitive programming challenges, and then also, by any organization that might want to have a combinatorial optimization task as part of their pipelines. So that was my last slide. Thank you so much for listening. Hope you've enjoyed it. And I'm very happy to stick around for some discussions afterwards. Thank you.
Thank you, Petar, for the fantastic talk. Tim, you have a question?
Yeah, I really enjoyed the talk. That was very interesting work. I just had a question about, you're saying this is a collaboration between human and machine. And I'm wondering what's the part in the last part that you showed, what's the human's role and what's the machine's role? So I kind of, the way you described it, it's almost like maybe the human sets up the scoring function and stuff, and then the machine just goes and does its thing. And the question is kind of, does that mean that, I don't know, most entrants to the competition could do just as well using that method? or is there more human in the loop along the way?
That's a really good question. I would say there is more human in the loop along the way. So it's kind of like the 80-20 principle. So yes, a tool like this, if you know how to write the basic greedy algorithm, assuming your competitors are just humans, without the use of an AI system like this, will get you in a pretty high part of the scoring function, and we've seen this quite consistently in all of the. Want to really like break into the top parts, or if the approximation to be possible, you will have to then iterate on what comes out of the system. The system might detect a particular pattern, which you then might want to use. So, for example, the system might have used some doubly nested for loops to investigate certain substructures. It might then mean that this is something you should incorporate into your backbone and just allow the model to explore more without having to like maintain this loop structure, which already makes it a bit more complicated to evolve. So yeah, and also trying out many different strategies. So certain strategies will be very easy for the model to evolve in. Some strategies will be basically a dead end because they'll plateau from the beginning. Like, if you put too much thought into your base solution, you might not be able to evolve much from it. So yeah, basically, I would say there's a lot of there is obviously some element of just monitoring the experiments and making sure that the model is not hacking anything, protecting your state in a better way, just mundane things like that, but also kind of being reactive to what comes out of the system and kind of iterating on the structure. We've done this a lot in the hashcode competitions. In the AHC competition at the end, we've only done the really rudimentary grid partitioning with different grid sizes, and I would say that's partly the reason why we're not ranked 1 on that particular contest. But yeah, so yeah, I hope that makes sense.
Yeah, thank you.
Matt, you have a question?
Yeah. So would it be unfair to characterize this as evolutionary optimization or genetic programming, where the LLM provides the service of sampling from the distribution over all programs? And if so, is it also, or where, I guess, where are the constants coming from? These are sort of very suspicious looking constants that arise in the program. Are these just constants that the LLM has seen in other programs, 1.00005, or are they directly being numerically tweaked by the evolutionary procedure?
So this is a really good question. I'm going to answer it from 2 angles. So first of all, yes, at least the way I think about this method, this is a genetic algorithm with an LLM as a crossover and a mutation function. So from that perspective, we completely agree. In terms of where are the constants coming from, I will tell you a little bit about some of the intermediate mutations that these systems produce. It gets quite interesting. So the model is going to stumble a little bit in this program search space, and many of the intermediate mutations might not make a lot of sense. Sometimes the model will just do idempotent stuff like multiply by 1 or things like this, or leave to-dos to itself, which is also really interesting. So it's a model trained basically on many big code bases, among other things. So it will be exposed to these kinds of artifacts. And we can argue that many public domain accessible codes will also have an element of, constant hacking whenever you have like a heuristic inside the model. So I would imagine, my hunch is, though I cannot like easily attribute it, is that the system has indeed seen how different heuristics are built in the wild. And I guess it sort of, interpolates an interesting crossover function from the wealth of human knowledge on how to build interesting heuristics. But that's the closest guesstimate I have. And maybe those constants could have themselves come from some combinatorial optimization suite, and then they were just hard-coded into the code base. But yeah, I don't have like a hard evidence of this. It's just kind of a hunch based on what I've seen in the intermediate mutation generations.
Does that answer the question?
As well as I suppose anybody could.
Suhas,
Hi, Petar. Thank you for your talk. Have a few questions, so let me try to get through them. So maybe you mentioned it briefly. I mean, I know you said it takes 2 hours maybe to get to a good solution, but how many LLM calls or how many steps of FunSearch is happening in these 2 hours?
Yeah, I would invite you to take a look at the x-axis of this plot here, where we have programs generated as the x-axis. So this you can think of as LLM calls, basically.
Okay.
Yeah. So you can see, like, for example, for flatlining on this particular problem, it depends a lot on the base grid size, of course. Smaller grids will give you more flexibility, but then you need more time. Some of the more coarse grids will converge in about 4,000 to 5,000 LLM calls, whereas the more fine-grained ones might require, 10 to 15,000 before they will stabilize.
See. Okay, thanks. Have you thought of, I mean, what happens if you take the first place solutions and then put it into FunSearch? Are humans already very good at generating solutions, or can it further improve on such problems?
Yeah, it really depends on the year. We haven't actually tried the exact experiment you've done, partly because we don't know often what the first place solutions are. I mean, this is not code that we have available to us unless the authors put it on GitHub, and it's hard to tell which code comes from where. But one thing we have noticed, let me try to zoom in. Oh, I can't zoom in. But if you look at the lowest right point in this plot, the mentorship and teamwork task from 2022, you can see that the y-axis goes up to 140%. So this is an instance where the evolving model has found a score which is significantly beyond what the top human team was able to do in that particular contest. And it discovered a relatively simple twist to what the humans were able to do, but it turned out to be pretty important for those particular test cases. And I think it should come as no surprise that these systems are capable of these kinds of things, because I mean, the capset problem is one example of this. Mathematicians have looked at this for a very long time, yet we were able to kind of improve the bounds just with a very simple, straightforward approach. So yeah, from time to time, I'm sure there will be problems that are just unsaturated yet on those particular distributions, and the system can basically do like a good takeoff and find the strategy that a human wasn't able to find. But according with my answer to the previous question, I still firmly believe that for the most part, this model is just doing interpolation on human designed heuristic strategies. So really, its skill sets will still be somewhat human inspired. And maybe there is some limits to that, but surely having access to a condensed collection of all human heuristic styles can be to your advantage in these cases, I guess.
Right. And finally, maybe more related to recent events, can you use such strategies also for improving, code generation for maybe what people think of as difficult code, like writing, GPU kernel code or things like that?
Yeah, totally.
Are
I
you
mean,
thinking of using these? Do you use these things for that?
I mean, I personally don't. I am sure there are groups that do, but yeah, I wouldn't be able to tell you more about how that works. But there's an evaluate function, there's a score function. The basic skeleton of FunSearch is open sourced, so this is something that in principle people can go out and play with if they have a good backbone to play with. So, yeah.
Thank you.
Hi, Petar. So I have a question on the broad scheme of things. So how generalizable are these algorithms that FunSearch is coming up with? And is there a way that you can actually control the computational complexity of the algorithms that are kind of produced?
Right. I mean, I'd say the answer is loosely yes. So one of the things that you can see that are kind of markedly different is, okay, so here are the scores for, say, a hash code qualifier round where you have visible test cases and you start to see all these weird constants emerging everywhere. That's basically the model overfitting to that particular test case, right? It's like it's learning how to solve that case really, really well.
Exactly.
And this is one style of contest, right? So in hash code, you know what the inputs are, and you just have to beat that input as good as possible. AHC is a contest where you know the generator for the tests, but you don't know what the tests actually are. They're hidden from you. And in this case, actually, where you have to optimize over many different randomly sampled sets, you actually start to get these kinds of, I mean, there's still a few constants here and there, but there are like broad strokes of strategies coming up, like this idea of fitting a Gaussian around a particular point. And similarly with cap sets, right? So you have cap sets for different dimensions. You have some kind of vague brush strokes of strategy in there that then, you know, the mathematicians use to actually find the new asymptotic lower bound. So I'd say it's certainly possible, but it depends on, you know, how much these models, you know, like any other evolutionary or kind of reward-based technique, they will optimize the hell out of what you give them in any way they can. That's one of the reasons why we actually struggled a bit, because Python is very loose about how much it protects its state. So we found, you know, cases where the model would just try to overwrite what the file reading function does and invent its own test case where it could amplify its score as much as it wants. So, you know, you have to be careful about these things. But yeah, if you give it a generic enough set of test cases, you should end up with a generalizable solution. And the second point I would make, which is controlling the complexity, currently we can do this by placing strict limits on the timeout and the memory usage of the algorithm, which is similar to what a competitive programming environment would do as well. Obviously, this is only a proxy for computational complexity, but you know, it can be kind of a nice first approximation.
But are there LLM solutions that can actually characterize and approximate computational complexity of a given algorithm?
I was literally about to say that I'm not currently aware of an LLM that can take a code and tell you reliably what's the complexity class of that code, partly because that might even be somewhat undecidable. But you know, I imagine such tools will get better over time, and you might be able to even use the LLM as an estimate of whether something is brute force or whether something is clever.
Any other question from the audience? Okay, we are exactly on time. So since we don't have any more questions, I think we can conclude here. So thank you so much, Petar, for the wonderful talk. And thank you so much for accepting our invitation as well. And thank you so much.
Yeah, thank you for having me. Hope you enjoyed it.
It was wonderful. Thank you. Bye.
Thank you.